Okay, students, let's start with this next session on heat treatment. This is session number 47, and here is what we are going to cover in this session. We'll talk about this heat treatment process, which is called normalizing. We'll try to understand what is its purpose, what are the main objectives of giving normalizing heat treatment to any steel, and then what is the procedure followed. And finally, we'll try to see as to what are the main points of difference between the process of normalizing and that of full annealing. So what is normalizing? You see, normalizing is a heat treatment process which generally is given to any steel component in order to refine its grain size if the grain size was distorted or had become coarse because of a prior treatment, and is generally also given to improve the mechanical properties like strength and slight improvements in hardness, etc. of the steel. This process is very similar to the full annealing treatment that we discussed in the last session, but this is a lot productive a process. It can process, it can heat treat the same batch of parts in far lesser time as compared to what full annealing would have taken. And also there are a few points which are different in it as compared to full annealing, and that would become clear as we proceed with this session. As I said, the main purpose or the main objectives of normalizing are: number one, to refine the grain size present in the steel. If the steel specimen was subjected to welding or heavy machining or any other process, any other prior treatment because of which the grains had become distorted or the grains had become very coarse, and because of these improper grains, if the mechanical properties had deteriorated, then normalizing is the treatment to refine the grain size. Normalizing is also used to make improvements in the strength and the hardness of a steel component. For steels which have carbon composition in the range 0.2 to 0.3 percentage carbon, normalizing is the best treatment which would bring the best machinability in this category of steels. Normalizing is also uh, used as a pre-treatment before hardening heat treatment. You see, hardening is a very complex and a difficult process, and hardening subjects the steel components to very testing conditions. So if the steel which is being given hardening heat treatment does not have a good microstructure in the beginning, the steel, if it had if the steel which is being hardened has got improper grain size, or it has a lot of internal stresses in it, or it has some other problems, and it is straight away subjected to hardening, the steel would fail during the hardening process only. So always when hardening heat treatment has to be given to any steel, normalizing heat treatment is used as a pre-treatment to set its microstructure, and then hardening is given. And also, students, in the last session we had discussed that full annealing treatment is never given to hypereutectoid steels. If full annealing is given to hypereutectoid steels, a very thick brittle network deposits itself on the grain boundaries, and this network is of cementite, and it severely impairs the properties of hypereutectoid steel. So whenever properties in hypereutectoid steels are to be improved upon, full annealing is not used, and it's the normalizing heat treatment which is always used for the purpose. What is the procedure for annealing? The procedure for annealing is similar to the procedure of full annealing, except there are two main differences. The first difference is that the temperature that we select for heat treatment is higher as compared to full annealing. Whereas in full annealing, if you remember, the temperature was 20 to 30 degrees in excess of the upper critical temperature, 20 to 40 degrees in excess of the upper critical temperature. Whereas in normalizing, the heat treatment temperature is about 40 to 60 degrees in excess of the upper critical temperature. And this comparison I am making for hypoeutectoid steels, right? Anyway, in case of hypereutectoid steels, when you do full annealing, if at all it has to be done, you don't even go till the upper critical temperature. You keep the steel somewhere in between the lower and the upper critical temperature. Whereas in case of normalizing, you go about 20 to 30 degrees above the upper critical temperature. So the temperatures in case of normalizing are higher as compared to what are in full annealing. And as a result of that, the austenite that you get is far more stabler as compared to the austenite that you get during full annealing. Okay, then soaking is almost similar, but cooling in case of full annealing was furnace cooling, equilibrium cooling, whereas in normalizing, the cooling is always air cooling. This cooling can be in still air, or if the specimen is fine, is good, then it can be even in slightly agitated air. So what is the procedure for normalizing? We'll take the steel specimen, we'll take the steel to this to the heat treatment temperature, which would always be above the upper critical temperature of the steel. We'll hold the steel at this temperature for some period of time, and finally we'll air cool the steel down till the room temperature. What is the microstructure obtained after normalizing? See, you need to understand a few things again in comparison to full annealing. The first point I had said is that in case of full annealing, the austenite that is obtained would be more stapler, because in case of normalizing, I repeat, in case of normalizing as compared to full annealing, because you follow a higher heat treatment temperature, the austenite that would be obtained during normalizing would be slightly coarser but more stabler as compared to what is obtained during full annealing. Mind it, this slightly coarser austenite will not have any impairment on the mechanical properties, but what is the significant difference then? The significant difference is that the austenite that has been obtained would be very, very stable. Point number two, during full annealing, you were doing furnace cooling, whereas during normalizing, you do air cooling. Now, the rate of cooling is faster during normalizing. What is the result? The result of this faster cooling is that the pro-eutectoid constituent that was to get formed does not get complete time to get formed as it used to get during full annealing. So if during full annealing, you can see from the iron cementite diagram that for any steel composition, what amount of uh, pro-eutectoid ferrite or pro-eutectoid cementite is getting formed. Since in normalizing, cooling is faster as compared to equilibrium cooling, that is the cooling followed during full annealing, so the amount of pro-eutectoid ferrite or pro-eutectoid cementite, as is the case, formed is lesser during normalizing. And point number three, students, if you look at the CCT diagram, when you do furnace cooling during full annealing, you land up in the austenite transformation region of coarse perlite. Whereas in case of normalizing, because you are doing air cooling, faster cooling, austenite transformation leads you to a fine perlitic region. So when you look at the final microstructure after normalizing, the final microstructure, if I specifically talk in terms of eutectoid steel, the final microstructure would be fine grained perlite with fine lamellar spacing. And how would the books write it? The books would write fine grained, fine perlite. So that fine perlite, the second part is that lamellar spacing is very fine. Lamellar spacing is very fine would mean a large number of lamellas of ferrite and cementite as compared to what were seen in full annealing would be seen in the perlitic structure in normalizing. And because a larger number of lamellas of ferrite and cementite are being seen, these lamellas would be finer, they would be less in width, right? So I'll show to you that first what is the procedure of normalizing. And here you can see that we are heating the steel to a temperature which is more than the upper critical temperature of the steel. Generally we go to 40 to 60 degrees above the upper critical temperature for hypoeutectoid steels, and for uh, hypereutectoid steels we go up to about 30 to 50 degrees centigrade more than the upper critical temperature. We soak the steel for some time, and right from here we start doing air cooling of the steel down till the room temperature. Okay, then what is the microstructure that is obtained in the steel after normalizing? You see, I discussed in the last session that what is the microstructure obtained during after full annealing. Because we are doing slow cooling, you see that austenite transformation product is fine perlite. Sorry, coarse perlite. And what does coarse mean? Coarse means lesser number of ferrite and cementite lamellas would be seen, and that invariably means that the width of these existing ferrite and cementite lamella would be very thick, right? But in case of normalizing, the cooling is faster than furnace cooling, it's air cooling, and you land up in the fine perlite region. So the grain size is still fine, the grain size is still what was here, no much difference. But look at the lamellar spacing, the lamellar number has increased, and also the width has decreased. So that is what is meant by fine grained perlite with fine lamellar spacing. That is what is meant by fine perlite. So students, I think the difference between normalizing and full annealing is clear. But the question comes, does that mean that normalizing can always replace full annealing? The answer is no. See, the major advantage of normalizing process over full annealing process is that normalizing is a very quick process. It's a quicker process compared to full annealing. So it's a far more productive process as compared to full annealing. So industry always makes use of this process. But then the question comes that also this process is less costly. And I discussed it in the last session that when you do full annealing for every batch, if you are doing furnace cooling in the furnace itself, then the furnace temperature is dropped till from 900 till 25 degrees centigrade, and again the furnace would be reheated to the heat treatment temperature. The fuel consumption would increase. This problem is not there in air cooling, because just after when the soaking step is complete, you pick all these specimens out and put them in open air. So the furnace is now free for the next parts to be processed. So normalizing is a more productive process. Normalizing is a more economical process from a process point of view. And that gives rise to a question that on all different occasions, can we replace normalizing to substitute for full annealing? Can we always remove a full annealing and use rather normalizing? The answer is no. If you want that your steel becomes very soft and ductile after the heat treatment, you cannot replace full annealing. Full annealing is the only process which can make your steel very soft and very ductile. Point number two, if you want that after the heat treatment your steel should be free from all type of internal stresses, residual stresses, locked in stresses, then also normalizing is not the substitution for, normalizing cannot do substitution for full annealing. Again, you'll have to use full annealing uh, over there. All other cases you can use normalizing instead of full annealing. So I hope students you have understood the things that we discussed here in this lecture. Thanks for watching.